In this class, we are going to discuss about static VI characteristics of a thyristor. So, this static VI characteristics of a thyristor, how are we going to see is something like this. Now, if you observe the main thyristor schematic, from there we'll talk about the static VI, and then it is having PN, right? Yeah. So this is PN, having junction J1, junction J2, junction J3, and this is considered to be as a anode. This is considered to be as a cathode, and so we are giving the supply in between anode and cathode. This is the supply, and the load we are giving here. So as we know that this is the junction J1, J2, J3, and then we are giving certain amount of gate supply here. So this is generally a pulses kind of stuff, and then we are giving here, and these two are connected to a common ground. Let me assume like this. Now, as you have already seen the characteristics of the static switching characteristics of the thyristor, how the thyristor is acting. Now we will go for, suppose let me take this thing. So let me assume that I have given the required amount of gate voltage to turn on the thyristor. Say this is my gate voltage that I am giving. So all these are time with respect to the second. I mean, these are the axis, the time scale with respect to this seconds, and this is the voltage in volts. So let me assume that. Now if I put some sort of voltmeter and ammeter here, this is the voltmeter where it will measure the voltage, and let me take, this is the ammeter where it will measure the current, So this voltmeter voltage I am representing as VA, and the current that is representing IA, and so I'll take I'll put one more ammeter here. So this resistance is simply to limit the current. I'll put this ammeter here, and I'll represent this as IG. IG means gate current. Now what is actually happening? So when you give the voltage, so immediately the current will not rise. It will take certain time, and then it will reach. So this current I am representing as a gate current. Now at this particular instant, so let me assume this is my gate current of 0.9 times of IG. This is 0.9 times of IG, and in this instant, if you observe the what is the voltage here, when gate current is trying to increase, when the gate current reaches to say basically 100%, then initially the voltage across this is high, that is equal to whatever the voltage that you apply, and then so whenever it is reaching at 90%, then the anode voltage starts decreasing. Something like this. So this anode voltage at this particular point, say whenever it is reaching to 100%, at this particular point the anode voltage is say 0.9 times of VA. So this is your anode voltage. Now slowly the anode voltage is trying to decrease, and then it will come to a almost 0 point, but there is a small drop. So we will consider the point that is at 0.1 times of VA is something like this thing. Now what is happening to this current? So let us see the current. Let me take the different color. Okay, so color is not coming. So let me take the current, and this current, same, all are in time scales. All are in time scales. This current. So when this anode voltage is 0.9 times, this current will slightly rise. So that means the current here is 0.1 times of actually anode current. So if you measure this anode current, whenever it is reaching 0.9 times, the current is 0.1 ampere. Now after a certain instant, like whenever this is reaching this 0.1 volts, the anode current is reaching say 0.9 amps. So there is a clear cut relation, and whenever it is almost zero, then the anode current will reach to full-fledged value. So like whenever it is almost zero, it is anode current reaching to its full-fledged value. This is the basic switching or turn on characteristics of a thyristor.